and programming languages. And some of those topics include the analysis of asynchronous and mixed synchrony systems, model checking, and software verification, and more recently on constrained counting and sampling in SAT and SMT problems. And most, over the last 5 years, he and his group have been working on this topic of Boolean functional synthesis, which they've written a sequence of really exciting papers on. And so I'm really delighted today that Supratik will be sharing these results with us on counterexample-guided repair in Boolean functional synthesis. Welcome, Supratik.
Thank you, Sanjit. Am I audible?
Yes, we can hear you.
Okay, great. So thanks, Sanjit, for the kind introduction, and welcome everybody to this talk on counterexample-guided repair in Boolean functional synthesis. This is joint work with S. Akshay, Ajit John, and Shetal Shah. I also want to say that some of you may have attended a couple of other talks that I have given as part of the Simons program on Boolean functional synthesis. So while this talk is, the focus of this talk is different from what I have covered in the other talks, some of the motivation and stuff are obviously similar. So hopefully there will be enough for you to stay tuned till the end of the talk. Okay. So here is a very generic view of synthesis, which is that we have a specification given as a logical formula, and this could be in any logic. For example, it could be in temporal logic, and we have some inputs of the system denoted in blue and some outputs of the system denoted in red, and we have a system to be designed which must satisfy the specification. So the goal of synthesis, automated synthesis, is to synthesize the system such that the specification is satisfied. But there is an interesting twist here that sometimes specifications are such that you may not be able to satisfy it for all possible inputs. And so we say that, well, you synthesize a system such that the specification is satisfied whenever it is possible. And I'm shortly going to give you some examples of this. So really what we want to synthesize are, this system has outputs which must be synthesized as some functions of the inputs, but then it need not depend on just the inputs. It can depend on the history of, what inputs and what outputs have shown up. It can depend on some internal state, which could be summarizing this history, and so on. So really we need to design the outputs Y as functions of perhaps the history and the state of the system such that the specification is satisfied. So just to be a little bit more concrete, here is a specific instantiation of this generic picture where I have a temporal specification, and this is for a very simple arbiter where I'm saying that these x1 and x2s can be viewed as requests, and y1 and y2s can be viewed as grants for a shared resource. So this is a simple specification which says that if indeed there was a request, then if there was a request from requester 1, at some point in time in the future, requester 1 should be granted the resource, and similarly for requester 2, and of course the resource cannot be granted to both of them simultaneously. And in this case, we might be interested in synthesizing the outputs as a function of, because clearly there's some history involved over here. I need to know whether somebody had requested, so that in the future I have to grant. So I have to synthesize the outputs as a function of the state, which summarizes the history of the inputs and the outputs. Now, a very popular and very effective way of solving these kinds of temporal synthesis problems is to use what is called the winning region calculation. So you basically find out the state space, of as different inputs and different outputs are coming, what is the possible state space you can have. So here I have just tried to draw some, hypothetical state space, not necessarily for this temporal specification. So there are states from which the inputs can come, and you have no control over these inputs. So these are the blue arrows. And then there are states from which the outputs have to be generated, and you do have control on how you want to generate the outputs. So these are labeled by these are shown by the red arrows over here. And a winning region is basically a set of states such that no matter what the environment does, no matter what kind of inputs come, it is always possible for you to satisfy the temporal specification. So in this particular case, let us say that these states shaded green constitute the winning region. And if you notice very carefully that, if a state, so let us say this state, and there are two possible ways in which the inputs can come, but no matter which way it comes, so for example, if it comes this way, you can generate this output and stay within the green states. If it comes this way, you can generate this output and stay within the green states, and so on and so forth for the other states. So this style of temporal synthesis basically says that, okay, let's first find the winning region in the state transition graph. And then we need to synthesize a winning strategy, which helps ensure that we always stay within the winning region, because as long as we are within the winning region, we know for sure that we can satisfy the temporal specification. Okay, and this is actually a very popular and effective way of doing temporal synthesis. But if you look at the core of this, there are these two steps. One is calculating the winning region, which involves some kind of reachability analysis on the state space. And the other is synthesizing this winning strategy to stay within the winning region. And what does this mean? So once you have the state space, and in particular, if you have a symbolic representation of the state space and the state transitions, we are basically saying that from every state, I should output Y such that the next state that I get from my current state and when I'm outputting Y is within the winning region. So if win region denotes a predicate which denotes the set of green states, and if next state is the transition relations, so that given a state and Y, it tells me what the next state is. And if both of these are symbolically represented, I just have one predicate here, which I should try to ensure that it always evaluates to true. So I have to synthesize Y such that from every state, this predicate, this entire composed predicate evaluates to true. The interesting thing to note here is that, although we started off with a temporal specification and which was used to get this winning region, but after we have obtained this winning region, and when we are trying to synthesize the winning strategy, there are no temporal operators here if we can symbolically represent the winning region and the next state transition relation. And the other important thing to note here is that it is not necessary that from every state you can synthesize a Y, which will get you within the winning region. So for example, this unshaded, uncolored state here is such that no matter what Y you choose, you're not going to come within the winning region. And so this is, a kind of important property of a lot of synthesis problems we try to solve, where the specification may not be satisfiable, in all cases. But nevertheless, whenever it is possible to be satisfied, we would like to generate the outputs such that our specification, temporal or otherwise, is satisfied. Here is another instantiation of the same template, and here I have a bit vector specification saying that there is a single input X, there are two outputs Y1 and Y2, and I want X to be the product of Y1 and Y2, the n-bit vector multiplication, unsigned integer multiplication, and I do not want Y1 or Y2 to be the vector representing the constant 1. So, if I view this problem once again over here, I have to synthesize Y1 and Y2 as functions of X. Once again, no temporal operators. And, this clearly means that Y1 and Y2 have to be non-trivial factors of this integer X. And once again, this is not always satisfiable, in particular if X is prime, because we have required that neither Y1 nor Y2 should be 1. And of course, if I could find an efficient solution for this, this would break crypto systems. This is just to say that this problem is not easy. Okay, so having said that, here is the formal definition of Boolean functional synthesis. I guess in both of the previous examples, we saw that, after a certain point, we are really looking at specifications which have no temporal operators and which may not always be satisfied. And so we're just saying, let's focus on these Boolean specifications on input and output variables. And I want to synthesize these Boolean functions for each of the outputs, such that for every input, if it is possible to provide values for the output such that the specification can be satisfied, then it is indeed the case that the specification is satisfied with these functions substituted for the outputs. And I would like to reiterate here that this form is also used for solving temporal synthesis once you have calculated the winning region and once you're focused on just generating the winning strategy. So although we are talking about Boolean functional synthesis, it has applications for reactive control synthesis, for example. And these functions fj are also called Skolem functions for the outputs in the specification. And we've already looked at this, that it may be the case that for some x's I may not have any y's, but still the problem is interesting as long as there are other x's for which I can find y's such that the specification holds. And for every x for which there exists a y, I should get the right thing. I should get the right value of y. And if I give you x and fx, it's actually easy to check whether there exists a y such that phi of xy is true, because from this definition, I know that in order to find out whether there exists y, phi of xy is true, I can just substitute the functions, and then you give me any value of x, I can just evaluate it to figure out whether it is 0 or not. Okay. So, and of course, there are other applications of Boolean functional synthesis. I'm not going to go over all of them for lack of time, but for example, certifying QBF SAT solvers have a lot of applications, and the Skolem functions we are talking about are of course certificates, and it can be used in program synthesis, repair of circuits, and so on and so forth. Now, for purposes of this talk, I'm going to focus on a particular paradigm, which is, really counterexample guided repair. But I mean, to sort of really give you the full picture, there are 3 steps involved in it. You guess some candidate Skolem functions starting from a Boolean specification, and then you check if your guess is correct or not. And if it is not, you get a counterexample. And then you've got to repair the candidate Skolem functions based on this counterexample. So this is the part on which we want to focus a little bit today. And of course, once you've repaired, you can send back the repaired Skolem functions, and then you can again check them, and this loop iterates as long as it is needed to generate the correct Skolem functions. And we will see that this loop must always terminate because of the specific way in which we repair the candidate Skolem functions. Okay. So, of course, when I'm doing this repair, I need to know a little bit about what are the things that I'm trying to repair. So what is it that I have guessed, so that I'm going to try to repair those. And so towards that end, we are going to talk, a slide or 2 about the guesses, so that we are clear about what we are trying to repair. So in order to do this guess, what I'm going to do is I'm going to fix a linear ordering of the outputs, let's say y1 through ym. And I'm going to, instead of trying to express each of the outputs as functions of the inputs x directly, I'm going to generate the last output, call it ym, in terms of x and all the previous outputs. So here I've shown the previous outputs in blue to intend to sort of suggest that I'm treating these, these are really outputs of the system, but I want to treat these as inputs when I'm generating the last output, so that from this specification x and y1 through ym, I treat x and y1 through ym minus 1 as inputs, and I just generate ym in terms of this. Now this is for the last output. What happens for the output prior to that? We say, okay, I'm going to generate ym minus 1 in terms of x and y1 through ym minus 2. And what will be the spec from which I want to generate this? I want to basically quantify out ym. I want to say that, look, this was my original specification. I don't want to bother about ym any further. So I'm going to existentially quantify it. And then I'm going to generate ym minus 1 in terms of x and y1 through ym minus 2. And if I continue this process, then, at the end, I'll get y1 directly as a function of x, because by the time all of the y through ym have already been quantified. And this, sounds like a reasonable strategy, except that there are these 2 subproblems that we have to solve. One is in each of these cases, I'm basically generating a Skolem function for a 1 output spec. In each of these specs, there is a single output colored red. And then I need to compute these, existentially quantified formulas. I need to do the quantifier elimination from this. And this is actually often quite hard to do these long sequences of existential quantification. So what we'll try to work with are approximations of these existentially quantified formulas. Okay. And then, it is not very hard to show that if you are able to generate y1 through ym as these functions g1 through gm, then you can sort of stitch them together to generate the f1 to fm that you were looking for. Remember that f1 to fm were only functions of x, whereas this y1 through ym are functions of x and the other outputs in the given order. And so it can be shown that there is just a small blow up in trying to go from these functions to the original functions. And therefore, it makes sense to just focus on computing these functions g1 through gm, and which really involves solving these two subproblems. How do I generate a scaling function for one output spec? And how do I compute the existentially quantified formula? How do I do the quantifier elimination, or at least compute approximations of that? Okay. Now for the single output case, it actually turns out to be very easy. I mean, if I have a single output, I can just set that output to 1, and then I get a scaling function, or I can set that output to 0 and negate, and then I also get a scaling function. And there is, a little bit of sort of working out shows that this indeed works. So there is no guesswork involved. If there's a single output specification, I can generate it straight away. Now, if there are multiple outputs, then we have seen that I need to quantify out some of these variables, and this can be a sequence of quantifications. This is hard in general, but I can easily obtain approximations of these quantification if I start from the negation normal form of the specification. And in fact, as I'm just going to show, that you start from the negation normal form of the specification, and if you set all the yi through ym leaves and the negation yi through negation ym leaves to 1, you get an over approximation of this quantified formula. And if you set the yi through ym leaves and the negation yi through negation ym leaves to 0, so this is kind of strange because I'm not treating yi and negation yi as negations of each other. I'm setting all of these leaves to 1, but it's okay to do this if I have the NNF form of the formula. And then this gives the under approximation. And then I can use these under approximations instead of the actual existentially quantified formula to guess the candidate functions gi, right? And of course, if I start with an over approximation, I'll get an over approximation of the candidate function. If I start with an under approximation, I'll get the under approximations. I mean, depending on which one of these I'm using. Here, starting with over approximations, I get over approximations, and here, starting with over approximations, I get under approximations. So here is just illustrating how this approximation works. Here is a simple specification, has some inputs x and some outputs y, and I want to existentially quantify out y1 and y2. So I've written out the NNF tree, and then since I'm trying to quantify out y1 and y2, I'm going to label all the y1 negation y1, y2 negation y2 leaves as zeros, and that will give me an under approximation. And if I label all of these leaves as 1, and that will give me an over approximation. So this is not very difficult. One just needs to work out, and it follows from the monotonicity of the operators in the NNF form. And so, this is pretty much what we are saying. So now the question is that, now that I have obtained these guessed Skolem functions, are they correct? And if they're not correct, how do I repair them? So given these functions, I need to check whether our definition of the Skolem function works. And it looks like we need a QBF solver, but we were able to show that one can really massage this formula a little bit and get a propositional formula which involves 2 copies of the outputs, y and y prime. And then if you feed this propositional formula to a SAT solver, then this propositional error formula is unsatisfiable if and only if the Skolem functions, the guessed Skolem functions, are correct. And if it is satisfiable, it gives you a satisfying assignment, which serves as a counterexample to the claim that the Skolem functions you guessed are correct. Because if you get a satisfying assignment, what this is saying is that for a given x, there actually exists some values of y which can make the specification true. But if you set the y's to your Skolem functions, the specification evaluates to false. So clearly, it means that there is an error in the guessed scaling function somewhere in some of the scaling functions. So how do we repair? Okay, so the counter example that comes out of this SAT call gives you a specific valuation of the x's and the y's, and you could say, okay, let me take those specific valuations and let me say that, okay, for those specific valuations of x, the values of y should be different. But this is not very efficient, because how many valuations of x? It could go all the way up to 2 raised to the cardinality of x. So we want to generalize these counterexamples. Okay, we want to find out, okay, from a given counterexample, can I find out slightly more counterexamples by generalizing it, such that I can then use the generalized counterexample to repair. So in order to understand how this generalized counterexample is obtained, what we're going to do is we're going to use these two quantities, delta I and gamma I, which are under approximations of these existentially quantified formulas we were looking at, with 0 and 1 substituted for the ith value of the variable. Now, remember that we figured out that there is a way to under approximate the quantified formula and also to over approximate the quantified formula. So here, if I want an under approximation of the negation of the quantified formula, I should really be over approximating the quantified formula, which is setting the corresponding leaves to 1 in the NNF form. So I basically obtain the over approximations of the quantified formula, negate them, that gives me under approximations of these formulas. Now, why are we dealing with these delta i's and gamma i's? It turns out that the guessed scaling functions were really the delta i's and the negation gamma i's. Remember, we said that these guessed scaling functions were just the one output specification case, where you just either set that output to 1 and take the formula as is, which is the negation gamma I, which is, these are quantified, and you just set the output to 1, or you set the output to 0 and you negate the specification, which is setting the output to 0 and taking delta I. So all our guessed functions are either gamma I or delta I. For different I, they could be different. And indeed, for the counter example, it sort of showed us that this guessed scaling functions are wrong. And so the generalization process, what it does is says that, okay, let me find out a function mu in terms of x and y1 through yj minus 1 for some j. Remember, this was the format in which we were guessing the scaling functions. So let me find out a function mu which generalizes sigma, in the sense that sigma projected on these variables satisfies mu, and mu also implies gamma j and delta j. Remember, we have all of these gamma j's and delta j's, which are under approximations of these quantities. And the moment I can find such a mu, and there are several heuristic ways to find such a mu, we can immediately say that this mu serves as a generalized counterexample for the guessed scaling functions. And why is that? Because if you look at the definition of gamma j and delta j, you will notice that if you conjoin them, you actually, basically you figure out that there is no way of setting values to yi through ym, which will make phi evaluate to true, right? So gamma j and delta j implies that for all values of yj through ym, negation phi will evaluate to true. So this means that there is something wrong with the values that we have set to g1 through gj minus 1, and no satisfying assignment of mu can be extended to satisfy phi. So this is the core idea how we do counterexample guided refinement. We generalize the counterexample to get a mu, and this gives a problematic assignment for g1 to gj minus 1, the guesses. And then I know that at least one of these must be flipped, because the counterexample generalized is telling me that there is some problem over here. And so what we do is we say, okay, let's try to find the smallest such j, such that I have this mu. And then we flip gj minus 1, because if I were to keep g1 to gj minus 2 unchanged, then indeed the value of gj minus 1 must be flipped, because I know that the entire tuple of values from g1 to gj minus 1 is wrong. Okay, and what does this mean? That if I had obtained gj minus 1 as negation gamma j minus 1, remember all the guesses were either negation gammas or deltas, then I need to add the mu, to this gamma j minus 1, and if this was delta j minus 1, I need to add it to delta j minus 1. So let me just wrap up by saying that this is the high-level idea of how we do counterexample guided repair, and note that this really involves expanding these under approximations gamma and delta. Every counterexample is generalized, and then the generalization is added to these, either the gamma or the delta, depending on what was being used for gj minus 1. And so therefore we also call this expansion based refinement. And this also gives us an easy argument to say that why this must terminate, because these expansions cannot go on forever, right? I mean, these are eventually under approximations of some quantities, and I'm adding more and more min terms to these quantities. I will eventually reach the quantities they were trying to under approximate. So, for lack of time, I'll just show some results and then take questions. So we have implemented this technique in this tool called BFSS, for blazingly fast Skolem synthesis. And we've compared this with a tool called KDIT, which is from Sanjit's group. And what we find is that, and KDIT of course uses a completely different, it makes use of CDCL style reasoning to solve the same problem. And what we find is that these two approaches are kind of complementary to each other. None subsumes the other. And so perhaps it's best to put them in a portfolio solver because, places where KDIT doesn't work well, BFSS with this counterexample guided repair works well, and vice versa. And so with that, I'd like to end because I've already run out of time, and I'll be happy to take questions.
Thank you, Supratik. Right on time. Are there any questions from the audience? Okay, let me start with a question of my own. So Supratik, do you think the ideas that you presented here can be lifted to a quantified SMT, like quantified bit vectors, synthesizing Skolem functions for quantified SMT formulas?
Yeah, so if you, one naive way and not the nice way is to blast the bit vectors and then everything is here. But that's, of course, not the nice way. So for bit vectors, this problem that we said solving for one Skolem, right, for one single output. I mean, if we could solve this problem, so if we could solve this bit vector problem for one output, and actually, I think a lot of the SMT solvers actually have instantiation schemes which allow you to solve this. CVC4, I think Z3, all of them have. So it can be bootstrapped based on the single output solution and then trying to quantify things out, but then you can work with under approximations and over approximations of those quantifications. So the short answer to your question is yes, but we have not gone to the point of building a tool which does it. Okay, and I'm sure there is a lot of gap between theory and practice when we try to solve such problems. So there are other things that are going to show up, right? So yes, I guess in principle the same techniques can be used, but because for the single output case we could use quantified instantiation techniques to solve it, and then we could use the over approximations and under approximations of the quantified formulas to solve it for bit vectors. In fact, this strategy should work not just for bit vectors, but for any theory where you can solve these two problems. Single output Skolem synthesis you can solve, and you can get over and under approximations of the quantified formulas.
Okay, great. Yeah, I think that extension could be really useful for some of the applications you listed on the slide, like program synthesis, for instance, right? Because just working at the bit level is a little bit limiting in that area.
Absolutely, I fully agree. Yeah. So we started some work on it, but we are. There's a lot more, as I said. There's a lot more between the theory and the tool, which we have to sort of solve.
Right. Okay. Any other questions? Okay, I don't see anything in the Q&A. So if there are questions, please put them in the chat or put them in the Q&A so that Supratik can answer them. Okay, thank you again, Supratik.
Sure. Thank you.
So that brings us to our midpoint today.